All right, everybody, let's look at molarity and how that relates back to the pH scale. So as we know, the pH scale is used to basically look at how acidic or how basic a solution is based on the amount of hydrogen ions there are in the solution. It's related to the pOH scale, which measures not the hydrogen but the hydroxide concentration in the solution. And you know, based on that word concentration, we should be able to tie that to our concept of molarity, because remember that molarity just has to do with the amount of something over the volume of the solution, right? And so we can actually relate the pH and the pOH scales back to the concentrations of hydrogen ions and hydroxide ions, and we'll be looking at the molarity of hydrogen or the molarity of hydroxide. And one thing that I want to make sure is pretty clear right at the beginning here, this thing here, H3O plus, this is known as a hydronium ion. And hydronium is basically, we use it the same way that we would use a hydrogen ion. The reality is that a hydrogen ion, which is just a proton, that is not something that just wants to exist by itself. It usually gets kind of snagged up by an existing water molecule, that even though that oxygen central atom on the water molecule is stable with its two hydrogen bonded hydrogen atoms, it's still pretty electronegative, and it will snag up that hydrogen ion to become H3O plus. But you know, really, when we talk about hydronium, if you just think about that as a hydrogen ion, that's totally fine. So anyway, just to clear that up. So if you have any one of these four items here, if you have one of these given to you, then you can easily find the other three by doing a little bit of math. And the math involves you using logs and inverse logs. And so here's like a little pathway that takes you from place to place. This is a little bit like our subway map in chemistry. So like, let's just say that, you know, we'll start over here on the far left. If you've been given the hydrogen ion concentration in a solution, you can find the pH of that solution by taking the negative log of that given concentration. What gets pumped out of the calculator is the pH when you do this function. From there, you can take the pH and subtract it from 14. That will get you the pOH. And then once you have the pOH, when you're going from a pH or a pOH back to a concentration, that's where you do the inverse log. And in this case, we are going to take the inverse log of the negative value of the pOH, okay? And then going back the other way, it's just as easy. Here we're starting at a concentration of hydroxide ions, and we're going to get our pOH by taking the negative log of that given hydroxide ion concentration. The pOH then subtracted from 14 will get you the pH, and then the pH, again, we're going from a pH to a concentration, and we got to use the inverse log of the negative value of the pH, okay? So let's do a couple of examples here. This is going to help you with your homework, and I wish we had like just days and days to talk about this, because it's pretty interesting stuff, but you know, this little mini lesson will at least help you with your homework. So let's just say that you are given a pH of 3.78. Okay, so if we have our pH and we want to get the pOH, we want to get the hydrogen ion concentration and the hydroxide ion concentrations. So remember, those concentrations, those are the molarities basically. And don't be afraid to see very, very low molarity of solution here. You know, we're talking about getting numbers with scientific notation with exponents as negative numbers, and that means they're really, really dilute concentrations. So anyway, the first thing that would be easiest to do would be just to find the pOH. Okay, so the pOH, remember, if we have our pH, we're just going to subtract that from 14 to get pOH. Okay, so let's do that here. 3.78 minus, oh, whoops, 14 minus 3.78. Okay, so our pOH is 10.22. Okay. Now let's use these values then to find our molarities. Okay, so the H3O plus, or our hydronium ion concentration, hydrogen ion concentration, we're going to take the negative log, inverse log of the negative pH value. So we're going to say inverse log of negative 3.78. And this is going to give us our molarity of hydrogen ions. So with the inverse log, I'm sure you've done this before. Here you just do second function log, and then negative 3.78. Oops. Okay, so this gives us a decimal that's really small, 0.0001659er, and we're going to put that in scientific notation, and so that decimal place is going to move 1, 2, 3, 4 places. So this is 1.65 times 10 to the negative fourth. Okay, that is the molarity of the solution in terms of its hydrogen ion concentration. So this is going to be the H. I'll just keep calling it hydronium, H3O plus. Okay, and then with the pOH, we're going to do the same thing to that to get our hydroxide ion concentration. So we're going to take the inverse log of negative 10.22, and that's going to give us our hydroxide ion concentration. So second function log, it's 10 to the power of, that's what the inverse log is, and then negative 10.22, and that gives us, a very, very small number. This is 6.02, I'll call it 6.03 times 10 to the negative 11th. Okay, and then so this is our hydroxide ion concentration. Okay, now we didn't do any log work because we really didn't have to do that. But let's just say that we want to go from, instead of, let's go from H3O plus, like let's say that we've got a given hydroxide or hydronium ion concentration of 1.55 times 10 to the negative ninth. Okay, so let's say that this has been given to you, H3O plus. Okay, and we want to turn that into a pH. So this is where you're going to use the negative log of this number here. So when you do a negative log, and just so you're aware of where we are on this little map here, we're starting here and we're just going here. So we're going to take the negative log of that number, and that's actually pretty easy. So we just say negative symbol log button, and then 1.55 times 10 to the power of negative 9, and that gives us a pH of 8.81. And remember that, so the pH of this solution indicates that this is a basic solution, not an acidic solution. So remember, when you get a pH of less than 7, it's acidic, and a pH of above 7 is basic. Okay, so I'll just show you this one more time. It's probably good to put this in your notebook or commit this to memory or whatever, and this will help you with 8.5 this year. And I'm, again, this is a lesson that we probably would have spent a lot of time on in class, but I think this will get you what you need to know. Okay, so I hope that helps, folks.